evening, everyone. Welcome to our 10th weekly discussion session for the Physics of Nanoscale Devices NPTEL course. I'm Jyotishwaran, a PhD student from the ECE department of IIT Roorkee. So, moving to the topics that we'll be covering in today's session, we shall be looking at the ballistic MOSFET. So, today's session is going to be entirely centered on the ballistic MOSFET, although the idea of MOSFET electrostatics is kind of started in this week. Again, questions do not feature in the assignment, so I shall be carrying that topic to forward to the next week's session. I did the same with the ballistic MOSFET from the last week's session. So our discussion will start from the end of week 9 and will go until just before the end of week 10. So the topics that we shall be looking at are essentially the Landauer transport model in a ballistic MOSFET, and using that we shall look at the linear and the saturation current expressions. So the idea here is to understand what kind of a dependence it has on the energy, or what kind of a dependence it has on these channel characteristics, and then we shall also revisit the concept of ballistic injection velocity and what role it plays in the behavior of a MOSFET. And finally, we shall end today's discussion with the notion of velocity saturation, which is kind of the mechanism through which a ballistic MOSFET enters the saturation regime. So, before we begin our discussion in earnest, the device structure that we shall be looking at, I'll just draw it on this slide itself. So the structure that we shall be considering is, we have two bulk contacts. So we have the source and we have the drain. So we have the drain, and these are of course connected by a ballistic channel this time. So this is a ballistic channel. Oops. Yeah. And in addition to this, there is also the gate. But what I would like to point out here is that we will not be seeing much about the impact of gate in today's discussion. So on top of this, we also have the gate. And so, as I mentioned, the impact of gate will not be studied as intensively in this week as we shall be doing in the next week, because the notion of MOSFET electrostatics is completely understanding the impact the gate has on a ballistic channel and what properties of the gate can be changed to bring about desired behavior in our ballistic channel. So for now, we can rest assured that there is a gate, and the gate influences certain things in our device. What those things are, we will see in our discussion. And it is also our understanding that typically the source is considered to be grounded, like the reference voltage is set to 0, and this is given VDS. On top of this, there is also a VGS here. So, but of course, as I mentioned before, we are not going to look much at the idea of the impact of VGS today. And in the presence of all of this, there is going to be a current that flows from the source to the drain. So this is the ballistic MOSFET structure that we will consider. So this is our ballistic MOSFET structure. And yeah, so I should be like calling back to this figure every now and then. So in today's discussion, again, if you've seen the assignment, there aren't very many numerical questions. So essentially, all of this is based on the derivations. So what we are going to do in today's discussion is we are going to start with some basics, and then we are essentially going to derive certain expressions. They will not be exactly the questions in the assignment, but hopefully they will give enough of a hint to solve the assignment questions that appear in that are present for this week. So the first expression we shall look at is the current in a ballistic channel. So yeah, so I should say ballistic channel of a MOSFET, because it's not the only current that can flow, is given by this expression. Now this by now we should be familiar with. So we have the transmission coefficient, as I mentioned before, and then we have the mode density function, and the difference of the Fermi distribution function in the source and the drain play a role in the expression for the current. So this comes from the Landauer model. So this is what we are going to use as a starting point. And the transmission coefficient is approximately lambda E by L. Uh, Technically, this is going to be a lambda E by lambda E plus L. But since lambda E is typically small, we can consider it to be this. And in the limit where L becomes very small, we can take T of E equal to 1. So this is the ballistic limit. And for a 2D channel, we know the mode density function is given by this. So here, what I've essentially done is I've taken this to be 2V of E by pi. Like, this derivation has been done at least twice in the discussion sessions alone. So you can go back and refer to them. And this h by 4 times this quantity essentially comes from looking at the energy broadening, which was seen to be uh, h bar upon tau e, the transition time. So from this, we arrive at this expression, and the 2D density of states is given by m squared by pi h bar squared. So combining all of these together, we will get this expression where B of E we write as square root of 2m star E minus EC. So here it is our understanding that the edge of the conduction band is considered to be the zero energy level. So this is the velocity as a function of energy. This plus epsilon 1 essentially states that typically our conduction occurs at a very small energy that is above the conduction band. So that is what the epsilon 1 over here suggests. Okay, so otherwise you can like take it to be E minus EC in most of the integrations. Okay, so this is just for the sake of propriety, because otherwise what will happen is typically even at the bottom of the conduction band the electrons are going to have some velocity. But if we take it to be this expression over here, it will tell us that at the bottom of the conduction band the electrons will have zero velocity, which is unrealistic. So which is why we have this epsilon 1 over here to kind of account for that fact. Okay. So, and adding this does not change the energy dependence of the mode function. So to reiterate, as seen before, m2d of E is proportional to e to the power half. That does not change. Okay, so using that, we'll go to like, so from here through the end of the session, we are just going to solve, like we are essentially going to be doing derivations one after another. And through the derivations, we shall also be discussing certain things. So the first is we need to derive the expressions for, okay, yeah. Initially this was written as two questions in one. So yeah, the expression for the charge stored in a ballistic channel, and then we need to derive the expression for the current in a ballistic channel that is operating in the linear regime. So these are the two things that we need to calculate. So first, we shall look at the charge. So part A is the charge in the ballistic channel. So now charge in the ballistic channel can simply be seen by the following expression. So the number of electrons n will be given by integral d of e f of e d. So this is fairly obvious because this gives the number of energy states and this gives the probability of those energy states being occupied at any given temperature. So as a function of temperature, we will have this kind of an expression. Now, since we are looking at a ballistic channel, we will, as we have seen before, the charge in a ballistic channel is given by uh, oh yes, here I should have mentioned 2D ballistic channel because our discussions thus far were for a 2D channel. So d to d of e times, now over here, if you go back all the way to, I think, week 3 of our of this course, this can be written as fs of e plus fd of e by 2 d, and yeah, let me extend this. Where is it? Oh, yes. Yeah. So now from this we'll get n is equal to integral 0 to infinity m by m star by h bar squared into, now let me assume that there is a VDS which is now just, since I know Vs is equal to 0, I can just say VDS is equal to some voltage V. I mean, even otherwise I could have fixed it to be a constant. Uh, so assuming that the source and drain are of the identical material, so over here I'm just going to assume that this and this are the same material, so they have the same Fermi level, which is almost always the case. So we will have times f of e plus f of e minus qb, because we are considering electrons here, so the charge of an electron is negative, so the Fermi level essentially comes down when a positive voltage is applied, divided by 2. Now, yes, so over here I should have written something more correctly, since I said EC is taken to be the reference. Just for that reason, I'm going to write this as EC over here also. So here again it is going to be EC. If you remember, I mean, if you had noticed, I wrote minus infinity to infinity here. That is kind of saying that we are integrating over all available energy levels. So here this essentially signifies that we are starting from the lowest available energy level. That is all. Doesn't mean that there is an energy state which has negative infinity energy. So that should also be understood. And that will also kind of be accounted by the fact that M of E below a certain energy level will vanish. So because those states don't exist. So that is also there. So because of that, this integral will automatically adjust to the point where modes become available. Okay. So these are just some like subtle things that ought to be remembered. Like they shouldn't be taken very literally. Of course, they are not mathematically inaccurate, but it comes with a certain understanding. So this is the lowest available energy. Yes. So now, again, what we can do is, I will just do that over here straight away, rather than writing it multiple times in the integral. So this is 1 plus e to the power e minus ef by kbt. So by, yes, there is a dE here. So if I set E by kBt to be eta, then of course dE is equal to kBt times d eta, and wait, yes, d is kBt times d eta, and from that what we can essentially do is, uh, and of course let me say I'm setting QB by kBt to be, uh, let me call this, what shall we call it? Let us call it eta v. Why not? Okay, so these are some things I'm doing off at the side before we arrive at the final answer. Okay, so we have this, and I just extend the slide. Ah, all right, and then of course, since this is this, I will have EF by kBt to be eta f. Yes. Let me see if I can do this. Yes. This is much better. So we have this, and yes. So taking all of this into account, what we will have is integral. This will become, so. Of course, I'm setting, yes. So rather than setting this to be 0, I will set, yeah, that will make the whole thing look better. I will set E minus EC divided by kBt to be eta, and here also it is not just E, it is actually E minus EC, because my zero energy level is taken to be, so this is E minus EC minus EF. This can be seen as E minus EF minus EC, so that is also there. Okay, so all of this will essentially tell us that we have m star kBt divided by pi h bar squared, integral 0 to infinity, 1 divided by 1 plus e to the power eta minus eta f plus f of uh, sorry, 1 by 1 plus e to the power eta minus eta f plus eta v. Yes. So dE. So now this will give us, of course, there is a factor of 2 here. So I'm putting that 2 out over here. So the final integral will come out to be m star dvt by 2 by h bar squared into, so this is the zero order Fermi integral of eta f plus the zero order Fermi integral of eta f plus eta v. So this is the total, sorry, this is the total charge stored in the ballistic channel. So this is the total stored charge. So from this we can say n is proportional to f0 of eta f, because I mean eta f, the variable doesn't matter. So essentially f0 appears. So it depends on the zeroth order Fermi integral for a 2D ballistic channel. So yeah, that is that. And of course, like under certain like temperature conditions, these two integrals will also become one. So we'll get that the total charge stored like at a given temperature will be given by this quantity. So that is the, essentially this is the number of charged particles. This is not the total charge, but the number of charged particles. Yes, this is not capital Q, this is capital N. So this is proportional to F0. Now, before moving on to the next part of this question, we can quickly see what will happen when the uh, uh, yes, in the saturation limit. Oh no, I'll go to the next slide and then discuss that. So, yeah. So now before moving on to the next part of this, what we should remember is when we studied our conventional classical MOSFET, linear regime is when VDS is very small. So VDS is approximately 0. I shouldn't say approximately 0. It is, well, it's very small. Okay. And saturation is, yeah, rather than saying VDS approximately 0, I can say VDS very much less than VGS. Saturation regime is VDS is greater than VGS. So these are the two limits that we consider when we look at the modes of operation. Of course, there is a threshold voltage also for the device to start functioning, before which it is 0, but that technically applies on the gate side of things. Now, one thing that we should remember is one of the key motivations for using, or rather for preferring to use nanoscale devices for short channel devices is that, so this I will just mention here, operate on low gate voltages. So this is one of the good feature, because this implies the amount of voltage I need to supply to my device to bring about the switching behavior is actually pretty less, which implies the power dissipated across my entire system becomes that much lesser. Like power and any kind of thermal effects and all of these things, as we shall see in our subsequent discussions, everything will become minimum. So that is one of the key motivations for picking up, or rather for even considering these nanoscaled devices. Just one second. Yeah. So that is the very reason that we are considering this. So in the case for a, so this is for a classical, yeah, I should have mentioned that here. So this entire thing is for, I wish there was an easier way to draw. I think I can actually lasso this. I don't want to. So yeah, so this is classical. Okay. But short channel devices operate on low gate voltages. So because of that, in a ballistic MOSFET, let me just have some color consistency. So this implies in a ballistic MOSFET, I can say linear regime is when VDS is very small, because since VGS itself is very small, I can substitute that by 0. So now I can say VDS is approximately 0, and then saturation regime is VDS greater than 0. So these are actually the two cases that we are looking at. Now, going back to our charge expression, even before we perform this integral, if we just look at this integrand over here, we have f of e plus f of e minus qv. Now the thing is, as qv becomes larger and larger and larger, what does this imply? This is effectively pushing the Fermi level further and further and further behind, like closer to E equal to 0. And at a finite temperature, we know that significantly far away from the Fermi level. So, in fact, I will even draw that here. So, at large voltages, what happens is the following. So, we have this. Yeah. So, this is our energy axis. This is the Fermi distribution function. So this is, say, at some finite temperature, and this is the Fermi level where it hits half. So this is EF, and let me say this is my Fs of E. Now, as and when a negative voltage is applied, this keeps sliding backwards. So Fd of E is going to look something like this for large enough voltages. And as we know, conduction occurs in and around the Fermi region. So conduction region is going to be somewhere over here. It's going to be somewhere around here, and symmetrically somewhere around here. So this is the region relevant for conduction. So this is what is relevant for conduction. And at this point, so the red one is FD. At At this point, we can actually see quite clearly that Ft is approximately 0 over here. So it has no bearing on the conduction part. So in the saturation limit, this part actually vanishes. So what we will be left is only F0 of eta F in the saturation limit. Okay, so what that means is kind of as Vd becomes larger and larger and larger and larger, at least insofar as the stored charge in the channel goes, it will kind of cap off at a certain point. Like it will, in truth, it will actually keep coming down. Like it will keep reducing. Like initially, the source contributes a certain amount of charge to the channel, and the drain, if it is at the same voltage, contributes the equal amount of charge. That is when eta V is equal to 0. As eta V keeps increasing, becoming higher and higher and higher, the drain contribution to the stored charge in the channel becomes smaller and smaller and smaller. And this makes logical sense because once there is a drain voltage, the electrons will prefer to stay in the drain electrode rather than in the channel. So the drain starts, for the lack of a better word, draining electrons from the channel. Okay, so I will also write that here. At higher voltage. So this is a matter of common sense, but nonetheless I'm writing it. Voltages, the drain ceases to contribute. Stored charge in the channel. This is due to not due to to the fact that the drain starts draining electrons. From the channel. So we are only using the things that we have known so far, but now that we are familiar with all these expressions and their properties, and we have seen these same formulae time and time again, now we can actually read into their significance. We can actually look at their like meaning in this context, like what they actually convey. So the first thing that happens is the stored charge in the channel comes down. Since the stored charge comes down, we can actually make another like further extended guess also, and I will come to this at a later point, but now I will just mention it. Just one more second. Yeah. So the thing is, we have also seen that the current can be written as like the charge present in the channel multiplied by their average velocity in the positive x direction. So since the charge stored in the channel kind of reaches a maximum, not a maximum value, it reaches a fixed value. It does not change after a certain point when VDS is increased. We can very well assume that it will impact the rate at which the current is increasing somehow. How that is going to impact it, we will see in a little bit more detail towards the end of today's session. But this behavior that we see right here also gives us a hint for saturation. So essentially, saturation, what should be understood is that saturation in a ballistic MOSFET is very different from saturation in a like classical bulk MOSFET. Okay, so yeah, now moving to part B. So part B of this question is, so here we need to derive the expression for a current, for the current. So We'll start from this expression over here. Now, as I mentioned, linear regime, VDS approximately 0. So this is linear regime. This implies, like, I'm not going to go into the full details of the derivation because we've done it to the death. So I will simply write the direct answer here. It is nothing but 2q squared upon h integral t of e m of e divided by dou e d e. So now I'll write this as 0 to infinity, just, or you know what, just for old time's sake, I will write it as minus infinity to infinity. Now that I've explained what it means into V. So this, as we have like seen time and again, is the, oops, so this as seen before. So so this is the conductance, and therefore from this we can simply say this is the quantum of, like, essentially this entire expression is the conductance. So this is, I shouldn't write this as conductance. I should essentially say this gives us the number of modes. So this complete integral gives us the number of modes, and this is the quantum of conductance. Which, as many of you might remember, comes out to be, so this comes out to be like 1 divided by 12.9 kilo. So this would be like what, 1 by 13, which is approximately point, should be about 0.07 something. So yeah, approximately it's 0.077 thereabouts. Millisiemens. So Siemen is the units for Siemen, or Mo is the unit for, yeah. So for people who are not like familiar with Siemen, sometimes, so this is spelled SIEMENS. So Siemens, or another unit is the inverse of an omega, which is pronounced Mo. So like the reverse of Mo. So yeah. So this is the conductance, quantum of conductance. This is the number of modes, and this is the voltage, which implies in the linear regime, as expected, IDS is equal to G ballistic times the applied voltage V, which is what we expect from a device operating in the linear regime. And we also know some special cases. For t equal to 0, we know that dou f by dou e becomes delta e minus ef. We know this to be true. Therefore, IDS at t equal to 0 is equal to number of modes, of course, like temperature is equal to 0 and my mode function T of E is equal to 1. I will also assume that. Then we can simply write it as M of EF divided by 12.9 kilohertz. So again, it increases linearly with the number of modes available at the Fermi level, and that is determined strictly by the material properties, which is the effective mass and the Fermi energy itself. So there is that. Oh no, this is the conductance times the applied voltage. Yeah. Let me just. This looks a bit cluttered. Multiplied by applied voltage, and here it is assumed that T of E is equal to. So this is the transmission coefficient. So this T is the temperature. Okay, so we have this. Yeah. So now we have seen how the current and charge varies in a ballistic channel, more precisely a 2D ballistic channel. This is an exercise that was presented in the slides itself, so it is a part of the lectures. So I decided I will work this out just to give a feel as to how things are changing. And giving this should also give us an idea of how the general behavior of these devices will be. So you've seen how things are there for a 2D channel, and now I will also look at it, show it for a 1D channel. Now that these two things are kind of present, you can guess what happens in the case of the 3D channel. Like, it should be easy enough to guess. Okay, so I will start that in a moment. I will be back in about 2 minutes. Yeah, so I'm back. So problem 2, as stated before, this is from a proposed exercise from based on a proposed exercise from Professor Vishwin during the lectures. So now we need to derive the current and conductance expressions for a 1D ballistic channel. So how do we go about this? So for starters, before we do anything else, we are going to need the density of states. So for that, we will need d1d v, and that is given by 1 by pi h bar m divided by 2e to the power half m star. Okay, so this is the first expression that we are going to need for reference. You can go back and look at, I guess, week 3 of this course. So this comes like way from the beginning, and a derivation had been presented in the lecture, and a different derivation was presented by me during the discussion session. You can look at either one, and we arrive at the same density of states expression for the 1D channel. So this is the thing. Now, what we need to understand is we need to get M of E. Now, to derive M of E, what we have to remember is M of E is nothing but gamma of E times pi into d1 d of E. This is the only thing that needs to be remembered. So, and yeah, so here I am talking about a ballistic channel. We shall not be looking at the diffusive limit. So T will not be appearing in our expressions. So we'll assume that this is a short enough ballistic channel where, so here I'm assuming T of E to be 1. Okay, so we are strictly in the ballistic limit. Okay, so this is the thing. And the energy broadening gamma E is given by h bar divided by tau of E, where tau of E is the transit time. So tau of E is the transit time. Now we know tau of E to be just length of the channel by B. So there is that. And here, of course, what we need to remember is, okay, so I should have, so this is this into the length of the channel, like length of the system. So that is, otherwise our density of states would have been written as G1D of E, which is the like density of states per unit length or per unit area depending on the dimensionality of the channel. So here there is already an L. So when I take h bar by this, essentially what happens is we'll be having an L in the numerator. So those two L's will kind of cancel each other out. H bar is h by 2 pi. So even that will kind of vanish. So what we have is essentially, and of course, oh yeah, I forgot. So the thing is, it is the average velocity in the positive x direction. Yes. So I should have written that here. This is not just v of e. This is v plus x of e. So this is the average velocity in the positive direction. Now we know that the particle can only move in the negative x direction or in the positive x direction at a given energy, because this is a 1D channel. So this quantity is actually literally equal to what I wrote before. This is just V of E, because there are no other degrees of freedom for the electron to have any kinetic energy in. Okay, so it can either move in the positive x direction or move in the negative x direction. Those are the only two choices. So if it is moving with that velocity, the transit time is simply the length divided by the velocity. So all of that together will give us this expression, h by 2 times d of e into, now this d1d of e will become g1d of e, so which will come out to be 1 by pi h bar m star by 2 e to the power half, and we know v of e is nothing but 2m star e by h bar square root in the numerator. So now you can see why I picked the 1D ballistic channel for our consideration, because what we are going to get is going to be rather convenient. So yeah, so this implies M of E equals, so this, if I enter it here, the 2e, square root of 2e, square root of 2e is going to cancel each other out. Square root of m and square root of m star and square root of m star will multiply with each other, and I will get a power of m. And 1 upon pi h bar is going to stay. Sorry, 1 upon pi h bar is going to stay, but yes, this is h bar here. This is not h. And yeah, so the only thing that I have to worry about at this point is the h. are the H's and H bars. So this whole thing, I will just write the whole thing just for the sake of completion. So this is, so I'm going to write this like this so that we know which cancels out where. Per half divided by H bar into 1 by pi H bar M star per half divided by 2e per half, and in this these two get cancelled out and these two multiply with each other, so that gives us h by 2. In fact, h by 2 pi, yes, h by 2 pi becomes h bar, so even one h bar gets rid of the other rather conveniently. So what we are left with is literally this m star divided by pi h. That's it. And you can see that there is actually some kind of a similarity here, because m star by pi h bar squared was the density of states for the 2D channel. Now we are seeing that a similar looking expression is actually the mode density function for a 1D channel. And this we already knew. We expected m of e, or rather m1d of e. I should write 1d here. Is actually proportional to e to the power 0. It does not depend on the energy at all. And this also makes sense because it is a one-dimensional channel. Doesn't matter what velocity it is moving with. As long as it is moving from source to drain, it is moving from source to drain. So nothing is going to change that fact. So this is m of e, which implies the things that we are supposed to find out for this are current and conductance. So IDS is now given by integral minus infinity to infinity. M of E is just this by pi h bar into Fs of E minus Fd of E dE. And since I'm asked for conductance, it should be understood that I'm in the linear regime, because otherwise conductance is not well defined. So this is well defined only in the linear regime. Okay, so there is that. So in the linear regime, we know what happens to this. Oh, of course, yeah, there is a 2q by h. That does not change. So yeah. Oh no. So this is the current. Now in the linear regime, so VDS approximately equal to 0 implies, now I can write this, IDS is equal to 2q squared upon h integral 0 to infinity, or rather minus infinity to infinity, m star by pi h bar dou f upon dou e dE This is a constant, so it just jumps right out into the applied voltage. And we move from the property of the Fermi window function that when integrated from minus infinity to infinity, the Fermi window function also integrates to unity. So that integral becomes 1. Therefore, IDS by V, which is the conductance, is equal to 2q squared upon h into m star by pi h bar. Now, I can, of course, acknowledge the fact that this is just h by 2 pi, so I can get rid of that. So the whole thing will come out to be 4q squared m star upon h squared, and so this is the conductance. So this is equal to G1D. So for all like 1D conductors, this is the thing. So just as an added exercise, what I'm going to do is I'm going to assume m star, like, so this I'm kind of making up on the go. So let me assume that this is that. So let us try to estimate what G is. Okay, so how much this is going to be for a 1D ballistic channel. As you can see, this is kind of becoming the only parameter this depends on is the effective mass of the electron. Everything else are universal constants. So this will come out to be, just 1 second, let me see if I'm using the right values. And we have the mass of the electron, which is this. Where is the Planck constant? Yeah, so this will come out to be, if this is the case, this comes out to be, this implies G1D will come out to be 0.23 Siemens, which implies the resistance of a 1D ballistic channel with this effective mass will be the reciprocal of this. So that will be 4.34. So, and as like here the temperature doesn't play a role, like in fact nothing is going to change anything in a 1D channel. That is the beauty of it, because well, nothing has much of a bearing. Like even if I consider the saturation limit where FD becomes 0, even then it is going to be integral minus infinity to infinity Fs, which is still going to be 1, and therefore the conduction is still going to remain, conductance is still going to remain the same. So the beauty here is, even if VDS is greater than 0, okay, I shouldn't have said the conductance remains the same. What I should have said is the current kind of, yes. So what will happen is, in the limit where voltage is very large, the current kind of saturates to the value of the conductance. Like essentially what will happen is, again, IDS is equal to, now let me just get all the constants out as 1. So that I can write it as 2q m star, or rather 4q m star by by h squared integral f of s of e minus infinity to infinity dE, and I know this quantity is 1. So the current essentially comes out to be just G1D divided by Q. So even that kind of fixes itself. So I don't even have to do much math to understand what the saturation current in a 1D channel will be. However, I don't know why that saturation is occurring, but by just taking the limit where this is very large, I can just perform this integral. Like this essentially comes out to be 1, and then just uh, what is it? Yeah, then just uh, like use this value here. So this will come out to be what will this come out to be? And wait a second, does this actually have dimensions of current? Maybe is that. So dE here, that is Q times V. Yeah, well, technically it does have the dimensions of current. Yeah, so I'm not doing this particular calculation. It will come out to be a very small value actually. So it will come out to be like, I don't know, 10 to the power, like it's going to be less than picoamps is the point. So in a 1D ballistic channel, that is as much, oh no, it won't be picoamps. It is going to be, sorry, I made a mistake. So it's going to be 10 to the power minus 60 over here, and it's going to be 10 to the power minus 50, and mm, oh no, yeah, saturation, no, it doesn't come out to be very small. It's a slightly large value, but, and that's the thing. And here also it kind of, we can see that it truly saturates. Yes, that is the point I wanted to emphasize here. This integral, no matter what the value of VDS is, after a certain point, this approximation holds. So increasing VDS actually does not increase IDS. So what is happening is whatever this value of current is, I don't care about that for now because I just don't feel like doing that calculation and it's not required. It will be linear up to a certain point, then it will begin saturating, and after that it will become more or less constant. So this is the behavior I will see in a 1D, like in a pure 1D device. Of course, those things don't exist. So when I have a 1D channel, and this is the output characteristic, so I have IDS versus VDS, and we'll see that in a 1D channel, almost true saturation occurs, like without any further provisions required. Okay, so there is that. Yeah, so that brings us to the end of problem 2. So this is essentially what Professor Vishwan wanted you guys to work out. So I've kind of done it here. There's a one teacher. So over here, I kind of know the slope of this because that gives the conductance, and then almost, it actually attains like proper saturation. Like typically we will expect it to have some kind of an increase due to DIBL effects or things like that. But in the Landauer model, at least as far as the Landauer model holds, proper saturation is very much a thing. Okay. So yeah, with that, let us move to a 3D ballistic channel. Now here we are not looking at the full current expression. Our aim is to find out what kind of a Fermi integral appears in it. So once again, for a 3D ballistic channel, we are going to write IDS is equal to integral. And the reason I'm solving these problems is if you can kind of track these things one after another, then more or less you should be able to figure out what appears, like if you look at your assignment questions, you'll see that the questions essentially ask what kind of a Fermi integral appears where for which kind of a channel. So if you just look at these examples, that should give you an idea of what kind of Fermi integrals will appear. Okay, so again we are back to our original current expression. It's a very bad infinity symbol. Yes, much better. So again, I'm assuming T of E is equal to be 1. So we have M of E times Fs of E minus Fd of E dE. So now we will need the 3D density of states. So the 3D density of states expression, again, like I need to be like kind of accurate here. So let me write this as G3D first is equal to M star to square root of 2M star E divided by pi squared H bar Q. Yeah, I think this is the expression. Yeah, I'm sure this is the expression. Okay, so now once again, M of E is equal to gamma of E divided by, so yes, not divided by, sorry, times pi into D3D of E. Now D3D of E is this quantity into the volume. Okay, so I will just look at this quantity first. So gamma is equal to, gamma of E is equal to H bar divided by tau of E, tau of E is equal to uh, length of the channel divided by average velocity in the positive x direction. Now this, I had done this derivation once before. However, I myself am unable to recall it right now. So let me just quickly do that. So for a 3D channel, we will have this kind of a situation where I have, like, this is the plane through which it is entering, and I have the velocity vector in this direction, which kind of makes, and let me consider the, yeah, this thing became a bit too parallel for my liking. So let me consider the plane that is, so this is to kind of know the azimuthal angle, because now there will be two angular dependencies. So when I have an arbitrary velocity vector that is stretching out in this direction, it will make a theta. So this axis is the x-axis. This is the direction along which I need to find the velocity. Oh, no, this is not the v, this is the x-axis. So this will be the z-axis and the y-axis will be into the thing. So this angle I'm denoting by, theta, and if I take the projection of this somewhere over here, then this angle will be phi. So I hope that can be seen at least somewhat. So this angle here is phi. So Vx is, so Vx of E is equal to V of E sine theta cos phi, and so now this thing needs to be integrated for it to be in the positive x direction. Theta can vary from 0 to pi, but phi can only vary from, phi is 0 at the x-axis. So phi can vary from minus pi by 2 to pi by 2. Okay, so first integral is 0 to pi, second integral is minus pi by 2 to pi by 2. So this is the phi integral, b of e, uh, sine theta cos phi. Now the volume element here is given by, it's essentially uh, r squared sine theta, sorry, it is, yeah, it is r squared sine theta d theta, r dr, r sine theta dr d theta d phi. So r is equal to 1 here. So we will have essentially sine theta d phi d theta. So now this will become minus sine phi evaluated from minus pi by 2 to, correct? Or will it be sine phi? Yeah, I got confused in the same place last time and I'm getting confused in the same place this time as well. So now this is going to be sine phi evaluated from minus, yes, sine phi evaluated from minus pi by 2 to pi by 2. So that is going to be 2. Yes, this is correct so far. So this is equal to, so this is my average Vx plus of E, and this will be equal to integral 0 to pi V of E. So this whole integral will give me a factor of 2. So the 2 comes out here, sine squared theta d theta. Now again I can take, what can I take this to be? I can take, of course, I can write this as 2 into 0 to pi V of E into, so 2 sine squared theta, sorry, 1 minus 2 sine squared theta is cos 2 theta, so this is 1 minus cos 2 theta by 2 d theta. So now I know integral cos 2 theta from 0 to pi is the same as integral cos theta from 0 to 2 pi, which is one full cycle, which comes out to be 0. And therefore, the only integral I have to worry about is v by 2 times this d theta, which will give me a value of pi. The 2 and 2 will cancel out, and what we are left with is pi times. Huh? Can't be pi times. It has to be, something has to appear in the reciprocal. Oh yeah. Oh yes, yes, yes. I'm sorry. So of course, in order for my integral to work, I will have to set 2 theta is equal to, some new angle variable like omega or something. So because of that, d theta will be this thing by 2. So yes. So I will essentially have another, just 1 second, I got confused once again. This seems to be an ongoing thing with me. So this comes out to be, yes. So there is a sine squared theta here, and this should, the answer should be less than v of e. It cannot be greater than v of e. Oh yes, the whole thing should also be divided by integral. Yes, that is the reason why all of this is happening. And I think this is, you can go back and see the previous videos. I'm sure I did the same mistake the last time. So pi by 2, yes, sine theta d theta d phi, yes. Oh, d phi d theta, because the integral order is kind of fixed. D theta, yes. So now this will be minus cos theta from this to this, so that is going to be 2, and this quantity is going to be pi, yes. So this whole thing is going to be divided by 2 pi, of course. Now this will be pi by 2, yes. So we are going to have 2 by 2 pi, or rather 1 by pi, 1 by pi into pi by 2, yes, times v of e, which will give us positive x plus v is equal to v of e by 2. This is kind of what we expect, like when we have complete three-dimensional motion, and if it can move in both directions, I will expect the average velocity moving in the positive x direction to be exactly half. So, and that is what we get. So this is the average velocity, which is what we will need here. So now this will become 2L by V of E. And therefore, gamma of E is equal to H bar divided by L 2L by VE, which is equal to H bar times VE divided by 2L, then, which implies the mode M3D of E is equal to, there is the volume term also, so I will write the whole thing first. So this is H bar V of E divided by 2L into pi into the volume. So this is the volume V. So I'll just, this is not the voltage, not to be mixed up. So this is the volume into m star square root of 2 m star E divided by pi star pi squared h bar cube. So one h bar and another h bar cancels out. One pi and another pi also cancels out, and L kind of vanishes. So what we'll essentially have is the area of cross section into V of E divided by 2 into m star into square root of 2m star E divided by pi h bar squared. Now what should be noted here is that V of E is equal to square root of 2m star E divided by h bar. So this whole quantity, like with one h bar, is actually E. So what we will have is A times m star V of E or rather b squared of E divided by 2 into 1 by pi h. And the keen-eyed observer will notice that this quantity is nothing but E. So the mode density function is actually area of cross section into the energy divided by pi h bar. And this is kind of what we expected because I know that M3D of E is proportional to E. We know this. So a factor of E has to appear somewhere, and this is what it is. And what we can also see is that the M star has somehow kind of been absorbed into this whole thing because of how we write V of E. So yeah, so this is mv squared by 2. So this is the energy that we are considering. So this is E by pi h. And of course, we are considered, so when we write the current, we usually look at current per unit area. So this A factor is also dropped. And the thing that we are supposed to find for this question is current expression for a 3D ballistic channel. So now, next slide. And therefore, I is equal to, IDS is equal to integral minus infinity to infinity. Of course, here now writing minus infinity to infinity is not good. So I'm going to write the proper expression here. It is going to be EC to infinity, and all energy was measured from EC setting EC to 0. So here E will be replaced by E minus EC divided by, so IDS divided by area of cross section is equal to this by h bar into Fs of E minus Fd of E dE. This is what it is. And from this, we can tell directly that IDS will depend on the Fermi integral of order 1 of E dash. So this is the first order Fermi integral that we will have to evaluate in order to find the current. And again, one can take all the linear regime approximations and take t equal to 0 and repeat all those exercises. I am not doing that. In fact, I'm leaving that to you. I've kind of covered how to do it for other cases before, and you can just straight away carry that forward. And so yeah, the thing to observe here is that all the expressions kind of line up rather well for 2D and 3D channels, which kind of makes us wonder why we considered, sorry, not 2D and 1D and 3D channels, which kind of makes us wonder why we considered 2D channels as the go-to example in our lectures. The reason is, while I would very much like to consider a ballistic 3D channel, such a thing actually does not truly exist. Because if all three dimensions are equally short, then the channel is more likely to behave as a completely confined unit, as 0D channel rather than a 3D channel. So a 3D ballistic channel is kind of a theoretical idealization, as is a 1D ballistic channel. But 2D ballistic channels and more precisely quasi 2D ballistic channels are a real thing. In fact, they exist in devices that are available, like state of the art devices. So there is, I mean, that is kind of the point why we have been considering the 2D channels. So the expression of current is over here, and the Fermi integral thing is also over here. And since now we know D of E has already been given here, people can also go ahead and calculate the total charge stored in a ballistic channel, see what kind of a Fermi integral appears there. They can repeat the same exercise for a 1D channel and see what happens there. I'm kind of, so the aim of this discussion session was to give one spot, like one set of slides where all the relevant expressions are present in one form or the other, which you can just quickly look up and do all your derivations in a short span. So that is the aim with which we are working. So now we move to the last part, which is the idea of velocity saturation. Before we discuss velocity saturation, I'd like to have a small, sidebar. Essentially, before beginning, I'd like to discuss some quantities. So, discuss some, not quantities, some concepts. So, when we consider saturation, classical. So, this discussion was done pretty exhaustively in the last 2 weeks. So, our idea is that we have this kind of a device in a bulk device. So like PMOS, NMOS kind of, that doesn't matter. What we have is, we have this, then we have our insulation layer, and then on top of that, we have a so this is the insulator, and on top of this we have our let me try a different color. Oh yes, this is a blue. So on top of this we have the gate. So this is the gate electrode, and I have the source, and the drain, like so. So what happens when we have, and so typically this thing is grounded, as is this, and here I'm applying VD. So when VDS exceeds VGS, what we say is that the channel that is formed kind of pinches off. So the channel that is formed kind of pinches off, and because of that, the channel for a classical MOSFET is the region where there is a non-zero electric field, which implies the electrons kind of accelerate through the channel. Now, after they exit this inverted region of the channel and go into the pinched off region, what happens is there is a lot of scattering. So in this region, essentially, so here scattering occurs, and this scattering kind of ensures that velocity does not increase any further. Even though there is a potential difference, the scattering counteracts it. And as VDS increases, the pinch off point moves further and further and further. So even though they accelerate, they gain a very high velocity at this point, they undergo an equally large amount of scattering and roughly arrive with the same velocity at the drain, which implies the current is more or less the same. So the idea is, in classical saturation, so this is a direct result of scattering. Scattering in the channel. So this should be like remembered without any ambiguity. Like the reason why saturation occurs is that there is a channel pinch off. Since the channel is pinched off, there are no more mobile carriers, like it is entering the medium, and there is a lot of like electron hole, all kinds of scattering that occurs. Like typically, because it is inverted, the majority carrier kind of changes over here, and that kind of can be seen as, not kind of, that leads to an increase in scattering in the pinched off region of the channel. So this is the pinched. precocious. Pinched, this is slightly more legible. Pinched off region of the channel. But such things actually do not occur in a ballistic MOSFET. In a ballistic MOSFET, like we have not discussed what the notion of inversion is, but nonetheless, the question remains, why do I have saturation behavior? Now, one thing I explained before, the amount of stored charge that is present in the channel kind of like comes down. Okay, so that of course will lead to a reduction in the current. But as I'm increasing the voltage, I would expect the velocity to increase. So there should be some way in which, like the idea is, I would expect the um, velocity to still increase, because as long as I'm applying a VD, then we go back all the way to the beginning. Like no matter how few, like whatever be the amount of charge here, if this voltage is increased, there is no scattering in a ballistic channel. So I should just get a kinetic energy that is equal to Q times VD. So it should just, keep increasing. Even though the number of charges stored kind of comes down, and I've told that it cannot go below a certain minimum value. So it should come to that minimum value, and after that, the current, I would expect it to still increase. So what is the reason that saturation occurs? So to understand that, what we will have to look at is the notion of velocity saturation. Like we will show that velocities cannot increase beyond a certain point, and that is actually, well, truth be told, it is a quantum mechanical effect. Like it is not even a classical effect, but we will be treating the thing semi-classically. So now our question is, how does and velocity saturate in a ballistic channel? So this is what we are going to try to address and answer in like the final part of today's discussion. Yeah. So yes. Now I know that the energy distribution is given by the Fermi distribution function. But what first thing I'm going to do first, approximation. That is why I said we are going to do this semi-classically at higher temperatures. Uh, and energies actually, because we are considering the saturation regime. So higher temperatures and energies, what I can say with confidence is that 1 upon 1 plus e to the power e minus ef by minus ef by kBt is approximately equal to e to the power minus e minus ef by kBt. So the Fermi distribution function becomes more or less similar to the Maxwell-Boltzmann distribution or the Boltzmann distribution. So this is the Boltzmann distribution. So higher temperatures and energies, so this is what we shall call the thermal limit. So we are considering a situation where like all velocities, all energies kind of become, not all, like higher values of velocities and energies become more and more probable. So now this is the uh, energy distribution. Now I also know that E is equal to half. Again, we are assuming that the velocities are still small enough to be non-relativistic. So relativistic effects are not being considered. Vy squared. So this is in a 2D channel. On top of this, I'm also considering the fact that Vx and Vy are not are. Yes, I can say are normally distributed. So when I say normally distributed, I mean they follow the Gaussian distribution. So that is what I meant by the thermal limit. Okay. Because previously we did not assume that. Previously we assumed that, like not previously, like when we considered the ballistic channel to calculate the positive velocity in the x direction, we kind of assumed that the velocity is uniformly distributed. Like, in the quantum limit, it can move in all directions with equal likelihood. But here, that is no longer the case. Here, what we are assuming is that the distribution is normal. So this is kind of is going to be centered. I will like tell you how it looks like. So now the probability distribution of Vx, Vy at a given E is going to be e to the power minus E minus Ef by kBt. In fact, at high energies, I can even drop the EF and I can simply just say this as, yeah, in fact, I should have done that to begin with. So this is E minus EC minus EF. So it is this quantity divided by kBt. So, and at high enough temperatures, even EF stops mattering. The only thing that matters is E minus EC. Okay, so same thing happens here. I will have E minus EC. Okay, so into, now the velocities are normally distributed, so that is going to be e to the power minus uh, yes, m star by 2 Vx squared plus Vy squared. So first things first, we can tell that in the thermal limit, average Vx of E, comma Vy of E, they're all zero, because this is a Gaussian centered around zero. Like the mean of this Gaussian is zero. So, okay, now we know that. And this is also kind of what we expect, because at high enough temperatures, when no external voltage has been applied, I would expect the average velocities of the electrons to be, because they cannot have a net positive velocity or a positive or negative velocity in any direction. Because without a voltage, I should not have any kind of current flow. So current should be zero, which implies, and we have electrons in the channel, so the velocity has to be zero, and that is kind of established by this. So now what I'm going to do is I'm going to give a representation. So now this is the variation of the axes are right here. I still somehow managed to botch that. Yes. And I apologize in advance for the awful looking Gaussian that I'm going to draw here. So this is going to look something like this. So this is a symmetry. Okay, so I'm not going to redo this. I don't want to waste too much time on that. So this is Bx, and this is, so what I'm doing is that this is a cross section. So this is f of Vx comma Vy comma semicolon E. Okay, so now at a given temperature and VGS, I have a certain number of electrons. So this complete distribution, like the total number of points under this distribution or the volume covered under this curve, like essentially what I will have is a 2D Gaussian. So if I look at this kind of like this, like I'm just sketching this diagram here. So what we will be having is kind of like a 2D Gaussian. So it is going to be, yeah, like actually drawing a 2D Gaussian without a wireframe is very difficult. So which is why I do the cross section here. Like the figure is present in the slides, so kindly refer to them. Lectures 48 and no, lecture 49 will have this. So you can look at that, which is the second last lecture of week 10. So understand that there is a similar Gaussian in the Vy direction also. Okay, and that kind of gives the 2D Gaussian structure. Now what happens when a voltage is applied? So here this is at VDS equal to 0. Now as VDS increases, what will happen is, again, in fact I can draw that right here. So what will happen is, and Vx greater than 0 implies movement in the positive direction. Vx less than 0 implies movement in the negative direction. Okay, so the sign of Vx also gives me the x direction. Now if Vds increases, what will happen is this will go slightly above. So now I will have a distribution like this, and this to compensate will go slightly below. Now, how much does it move above and how much does it move below? That is the next question. The answer to that comes from the fact that me applying a VDS does not introduce any new charges into the channel, because that is controlled only by the gate voltage. So no matter what happens, this velocity differential will not change the number of charges that are present. Therefore, the volume under this curve, this surface will not change. Or in the 2D scenario, the area under this curve is no longer going to change. Okay. So that is the point that we are supposed to consider. So yes, now looking at the Gaussian. So if I have a Gaussian of the form e to the power, so now I'm going to write some properties of the Gaussian function. So minus infinity to infinity e to the power minus x squared. Oh yes, did I put a minus sign? Thank God, I put a minus sign. Yes, it's right here. Otherwise, it would have been catastrophic. So yeah. So now this is going to be e to the power x squared by c. Like this is the one that I'm going to consider. Yeah, e to the power x squared by c, yes, by c is equal to um, square root of 2 pi into, oh yeah, c squared, not c, mod c. So this is what we will get. Now, of course, here I'm integrating only with respect to x. Yes, I should have written dx here. So if I look at this function, I'm going to assume, not assume, I'm going to say that this remains a constant, even if I change VDS, because changing VDS, okay, well, changing VDS will technically also change this. Oh no, it won't. It will only change Vx, but Vx squared plus Vy squared will still be a constant. Okay, so it is kind of pushing the electrons in one direction. So, well, sorry, I made a mistake. So this thing will change. It will, but right now I'm kind of neglecting the changes. Apologies. The previous statement I mentioned was wrong. For now, I'm kind of neglecting this. Right now, I'm only concerned with this shifting. I want to see how high this thing can go. So first, this implies then integral minus infinity to infinity e to the power. So the Vy part, well, I can even write the Vy part. I mean, doesn't make uh, uh, any difference because it is the same for both. So e to the power minus Vx squared plus Vy squared divided by 2 by m star dvx dvy is equal to, now there are two Gaussians, and like if they're, as long as they're independent, this integral will also kind of square itself. So this thing is equal to 2 pi by, like it will split out into the x and the y parts. So I will write them as two separate factors, because at a later point only one of these distributions is going to change. So that is going to be square root of 2 pi times mod c. So this is going to be into 2 pi m star per half into whole square. Okay, like not into whole square, the whole thing squared. So one is for Vx, the other is for Vy. Now, as I'm applying a VDS along the x-axis, the Vy distribution, I will expect it to not change. That is a fair enough assumption to make. The electric field applied along the x-axis will only give an acceleration along the x-axis. So the distribution of only Vx is going to change, whereas Vy is going to remain the same. So now, and from this we can also find out one more thing. The Gaussian is symmetric. This implies integral 0 to infinity e to the power minus x squared by c squared is equal to half of this value here, which is nothing but square root of pi by 2. That's not c. Okay. So now the thing is, I need to find out, like, so yeah, yes. So now I'll tell you why I wrote this here. In the limit where saturation occurs. So when saturation has finally, velocity saturation has finally set in, what will happen is this part will become nearly flat. Like there will be almost no electrons moving in the negative x direction, and all the electrons will have a positive x velocity. So we will have a situation like this. Now the thing is, even this green curve has to have the same area under the curve as my original Gaussian. So that is the catch, and that quantity is given by this, which implies, oh yeah, next slide. So complete saturation, complete velocity saturation implies integral 0 to infinity e to the power minus Vx squared. And now I'm only going to write the Vx Gaussian, Vx part of the Gaussian. So Vx squared by 2 by m star multiplied by a constant, because remember this is now just half of a scale. Like this is the Gaussian becomes higher and higher and higher, but only half of it exists. So this is multiplied by a constant and an integral is done only over half. Okay, so c times this has to be equal to root 2 pi into 2 by m star per half. Like this is what I would want. Now I know this integral is e to the power minus, oh no, why am I writing the integral again? Now from, of course, dbx, not to forget that. Now this is c times half of this. I've written that here is pi by 2 times mod c, so that is going to be root pi by 2 into, so this is square root pi by 2 into 2 by m star per half. So from this we'll get c is equal to 2. This implies c is equal to 2 because it has to be twice this. So in the limit where complete velocity saturation has occurred, this Gaussian will become twice as tall in one direction, which also kind of makes sense because this whole thing is going to get added to this side. So that will tell me that at x equal to 0, this function will now have twice the value. So at x equal to 0, initially it had value 1. Like the whole thing is considered to be normalized. Now it will have a value of 2 instead of 1. Okay. Then and only then will the area under the curve remain a constant, and the area under the curve in this case represents the number of electrons, and that is not changing. Okay. So now we need to find out the average Vx of E. Rather, yes. So let us first find this Vx plus of E. So now that is nothing but integral 0 to infinity 2 Vx e to the power minus Vx squared by 2 by m star dBx. Now again setting mvx squared by 2 to be some quantity t. This implies 2mvx dvx is equal to dt. So like I'll have to multiply and divide by m star. So this thing is going to be integral m star oh no, 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 no. I will have to write this as, yes, so I will have to write this as square root of, yeah, that is where I was making a mistake. So multiplying and dividing by, yes, yeah, this is fine. M star times e to the power minus t dt, right? Wait, oh no, 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 I'm sorry. So what I should have done is, I should have written, yes. So what I'm going to write is the following. I'm going to write this as, again, this is just an estimation. So we have m star by 2 whole power half into v the whole square into vx is equal to t. I'm going to set this to be t. Okay. Now if I say this is equal to t, then dt is equal to, yes, or rather dv is equal to, dvx is equal to dt divided by uh, square root of 2 by n star. So now this is going to be again uh, t divided by 2 by n star, yes. So this is 2t, yes, 2t times, again there is a no, vx will be equal to t divided by m star by 2 square root, and this is going to be, so the whole thing is going to be divided by 2, yes, so this is going to be m star t. M star t e to the power minus t squared dt, yes, and now I can do the further substitution. And previously also I would have arrived at the same answer. So now I can set t square is equal to some new variable, so that implies 2t dt will be d of that, and this is e to the power minus x. So finally I will get the velocity to be m star times uh, yeah, m star by 2. Yes. So this will be in the normalized units. So here like n star by 2 might look like a very small number, but the thing is this whole thing has been normalized by a certain factor, which is the number of electrons. So if you kind of combine those two, this velocity will be like a, and there is also my, e to the power minus e by ec thing. So this is v of e, which seems to be a constant. Now the complete average velocity, yes, so this will come out to be, yes, m star by 2, and from here if I want to find the average thermal velocity, which is Vx plus, like the saturation velocity, this is going to be integral e to the power e minus ec to infinity, m star by 2 dE. Now here we should remember that dE is, well, how do I go about this? So yeah, yes. So now this will again be another Gaussian. Yes, because E minus EC is what we approximately write as, not 2, is m star v squared by 2. Like this is the total velocity. Okay. So now dE therefore is going to be, again I will set E minus EC to be some dE dash. So dE dash is going to be uh, m star v dV. Okay, so there will be a 1 by v factor over here, and then when we perform the full integration, we will arrive at our old expression where I will have 2 kBT divided by, yes, there's a factor of kBT also here, forgot that, by pi m star. So this is the average, like, saturation velocity. This is the, no, not the average. This is the, yeah, this is the average. Essentially, when I say average, this is the thermal saturation velocity, which is what we like derived as the ballistic injection velocity. Like for low enough temperatures, we wrote it in terms of like the Fermi, like, so we essentially wrote ballistic injection. The injection is equal to this quantity, square root of 2 kBT by pi m star. Yeah, the reason I'm hurrying on is like this session has gone on for a bit too long. So, but you can like evaluate these integrals and find out what is what. Okay, so this was f of half of eta f divided by f0 of eta f. Of course, f0 of eta f comes out to be 1 because it's the integral of the Fermi function itself. So this quantity here is the ballistic injection velocity for a 2D channel. So what we have here is for a 2D channel, when the temperatures become very high, this quantity also becomes unity. And this is the saturation velocity. So this is the highest possible velocity electrons can have in a 2D ballistic channel at like very high temperatures. So this value approximately comes out to be, I think, 1.2 into 10 to the power 7 meter per second. So our assumption that this whole thing is non-relativistic is relatively valid because we are not getting very high velocities. 1.2 decimal point should be seen. And this is kind of the reason why velocity saturation occurs. That explanation was given here itself. The reason why velocity saturation occurs is that there are only a finitely many electrons present in my channel. So, and I can only give them so much energy. Because even if I have infinitely high temperature, all, like, okay, only at infinitely high temperatures can I assume that all electrons have the same energy. At any finite temperature, there is going to be some kind of variation, and that variation is given by the Maxwell-Boltzmann distribution. And because of that, the average current that I'm going to receive will kind of get capped at a certain point. So the velocity saturation occurs due to the fact that there are only so many charges that can be present in my ballistic channel. And to increase that, we will need higher and higher values of Vg, but even that will stop at a certain point because remember that these are small scale devices where the total available number of energy states is finite. So even if we increase Vg, it will only increase up to a certain point, and after that even that will stop because there will literally be no more energy states. Like the complete density of states will be like filled for a given 2D channel because it is kind of independent of energy. So the only other way I have to like increase the charge present in the channel is to like raise the temperature further and further and further above. But in that case, our devices will no longer work in an ideal fashion. So that is not an ideal thing that we would like to consider. So typically we talk about small, relatively small finite temperatures. So in that limit, this phenomena is always going to happen, and because of this, the velocity saturates. And this is the reason why we see saturation behavior, not scattering, as was the case with the classical devices. So with this, I bring today's session to a conclusion. Um, and so one more thing is we will be having an extra discussion session which will happen after week 12. So in that session, I intend to discuss all the assignment problems, not all of them. Like I will discuss essentially concepts from the assignments themselves to highlight what are the important results that may require to be that may be important in the exam and things like that. Like of course I don't know what the exam questions are. Like that thing is not accessible to me. But nonetheless, what from my experience, I will tell you what are the important things to remember, what parts of the course people need to pay attention to, and so on and so forth. The exact date of that session has not been fixed yet. You will be notified about that pretty soon in the course webpage. I thank you all for listening. We will meet next week, same time, for the next week's discussion session. Thank you.